Okay, I've got a couple of videos here involving problems with graphing, and I'm not going to write out all the data on the iPad, although if you're using Excel, I recommend you do mostly just to see if there's any major variations in the slope or the intercept. But 9.9 says it's a reaction in the aqueous phase was monitored by absorbance of a reactant at various times. So kind of using spectrophotometry. We use SPEC20s in the old days, or you could use the UV vis and watch the reactant decay over time, not unlike the lab we did the other week with the ion we watched decay. Essentially, this question is asking, how do you use that experimental data to figure out what the order dependence is? And so I wrote a little summary here of the plots that you've learned to determine if you have some reactant A going to products. Zero order dependence will give you a line if you plot the concentration versus time. First order is the natural log of the concentration versus time, and second order is 1 over the concentration versus time. It turns out, if you use Excel to do this plot, you will get a linear plot for the natural log of, in this case, absorbance versus time. Just want to point out that because Beer's law has a linear relationship between concentration and absorbance, it's okay to use absorbance as a substitute for concentration here. Notice that the slope of the line is the negative of k, so we expect a line in that direction, and my data shows here that the negative of the slope turns out to be 1.71 times 10 to the minus 3 seconds inverse. Please note that depending on the order of the reaction, the units of the rate constant are going to change. So I'm just going to call this A. So a rate law for this expression would be something like K times A to the first. Again, I'm not using A's in this. I'm kind of overusing A here. And we actually have a numerical value for the K, so we could go on to do problems that involved half-lives or trying to find the concentration at some later time. So that's 9.9. It looks like I have a positive value here. Looks like I need that over there. 9.10 presents to you a gas phase reaction where the partial pressure of the reactant is kind of a proxy for concentration. So you would do the same thing here. You would plot pressure versus time, or natural log of the pressure versus time, or 1 over the pressure versus time, in order to get a linear plot. It turns out that this one is also first order based on the data we've given you, and this K turns out to be 1.19 times 10 to the minus 4, again second inverse because it's first order. And finally, 9.14 asks you to look at zero order reactions. Here's the integrated rate law. The important thing to know about zero order reactions is that there's no dependence on the reactant. So that basically goes away. If you were to plot, for example, the rate of the reaction versus the concentration, you would just get a straight line because it's not going to depend on A at all. If you look at the integrated rate law, and remember something I mentioned from the earlier slides, if you plot the concentration versus time, you are going to get a straight line decay. The slope is equal to negative k, right? And did I get that right on the previous? And the numerical value here on 14, actually this is just a thought problem, there's no numbers involved, but the rate constant is just going to be the negative of the slope. And it asks you to think a little bit too about the half-life. Well, there's a couple of points here. The definition of half-life is that it's the concentration when the original concentration has been halved. So based on the equation at the top of this slide, you could see that if you solve for k, you get 1 over 2 times the half-life times the original concentration. If you think about it, though, because there's no dependence of the decay over time, only 2 half-lives can occur. Because if whatever your concentration was is exactly halved after a certain amount of time, well, you're going to end up with exactly 0 of the reactant in twice whatever your half-life was. So only 2 half-lives can occur in a zero-order equation. I'll post this and some others as I get time a little later in the afternoon.